lecture some aspects of mathematical philosophy. And today we are going to talk about the use of visualizations and thought experiments in mathematics. Okay. So, let me repeat myself in terms of what things we are going to focus in these lectures. First of all, it's mathematical practice, as I already said in the previous lecture. Current mathematics examples, case study from current mathematics, the role of cognitive representations. Here, maybe it's a new word for you, cognitive representation. I mean a representation which is a visualization or a thought experiment, something which I contrast with mathematical representation. Yeah? A contrast between an abstract object, a mathematical object, and a representation of this abstract object, a physical object, a drawing, or it could be an object in imagination, a thought experiment, for example. Is it clear so far? Is it? Yeah? Okay. So, thought experiments, they are experiments which are run in imagination. Right? And I should say a couple of words about history and variety of thought experiments. Unfortunately, I have not much time, and I think there is extensive literature nowadays on thought experiments. You can read it. It's available. Most of things are available online or in books. Nice articles, and I have in the reading list and the introduction of the course, I have some references. But I don't have time to go through. I would rather focus on mathematical thought experiments today and give you a case study so that you have a clear, more or less clear view what it could be, mathematical thought experiment. Just a couple of words about the variety of thought experiments. You can find thought experiments in physics. Einstein was very creative in terms of producing thought experiments. Things like traveling on the ray of light, and there is Schrödinger's cat, and Einstein's lift. All these things you can find online. There are thought experiments in philosophy. Do you know some? In philosophy of mind, Chinese room, yes, Jackson's Blind Mary, yeah. Well, Chinese room, or even Turing test is a kind of a thought experiment, isn't it? That you have a computer and you have a person and you can distinguish their behavior in terms of interacting with a third person. Anyway, you can find thought experiments in philosophy, in science, but you can also find them in mathematics. People tried to give a definition of thought experiments, which turned out to be quite difficult. So it's good that we have a variety of examples which helps us to understand what it is. There are attempts to classify thought experiments by the main features. But as I said, we will focus on mathematical thought experiments. So, what are the main characteristics of thought experiments? Of course, they have some kind of experimental character. Yeah, usually it's a question, what might happen if? What will happen if? Yeah. There is experimental scenario running in a thought experiment. So usually a thought experiment starts with words, imagine that, blah blah blah, and then you can see what happened. Often a thought experiment is accompanied with diagrams, and some perceptual experience is usually required. Like you have some sensory experience, you can imagine, you can see it visually, maybe you can touch it in your imagination, maybe you can do some manipulations like stretching it or breaking it or doing something with it, maybe even smells, maybe colors could participate in this scenario. What are non-thought experiments? Well, things like counterfactual, hypothetical thinking. Not all of the cases of counterfactual, hypothetical thinking. What if? Yeah, what would happen if? Would count as a thought experiment, right? Given that we need this scenario running, yeah, and this kind of physical properties involved. Of course, things like computer proofs would never count as a thought experiment, or something similar to computer proof. And also, imagining, just running in your imagination a real thought experiment is not really a real experiment. Yeah? It's not really a thought experiment. Yeah, it's just a real experiment which you run. Well, you can argue about this point, but it would be more interesting to talk about experiments which are really run in imagination, not in reality. In philosophy, there is an extensive discussion about the role of thought experiments in sciences, or in philosophy, or in mathematics, and in particular epistemic roles. So the question is it possible to discover some new knowledge without involving new resources? So you are sitting in a chair and you are imagining something, some scenario of an experiment, and all of a sudden you are getting something new, some new knowledge. Could it be possible? So some people say yes, it is possible. It's extraordinary, but it's possible. And some people say no, it's impossible. James Robert Brown, whom I mentioned in the previous lectures, he defends an important epistemic roles of thought experiments and visualizations in mathematics. And his position is very strong. He claims that thought experiments and visualizations in mathematics, of course some of them, are proofs, and they are different from mathematical formal proofs. Yeah? They're a different way to prove the same thing. So this is a very strong claim, as you can see, and it has some difficulties. For example, some people say, well, what we shall count as a proof in this case? There is kind of a double standard of what proof is. On the other hand, quite often you can formalize a thought experiment or a visual argument in formal words, yeah? And it could be really different from a standard mathematical proof, a combinatorial proof, for example. One of the main objections is put forward by John Norton from University of Pittsburgh, Norton published a paper in 1996 which is called "Are Thought Experiments Just What You Thought?" And his idea is thought experiments are simply hidden, picturesque arguments. So, which means they don't really bring anything new. So his idea is there is an argument, and you just wrap it in a nice pictorial way to make it sort of better understandable, comprehensible, brighter, kind of nicer, more interesting, more amusing. But what is inside them is just an argument, a logical argument. Nothing more than derivation from some premises, come to conclusions. So all these physical properties, smells and colors, are just a furniture, just to make it more looking nicer, looking pretty and more interesting. So, from involving physical properties, imagination, visualizations, you're not getting anything new. You already have a logical argument. That's it. So this is Norton's objection, and James Robert Brown, he published a book, The Laboratory of the Mind, which is devoted to thought experiments in science and in mathematics. The first edition was published in 1991, and after extensive polemics with Norton and other people, other philosophers, Brown published the second edition when he prepared a better replies to this objection. His main reply to Norton's objection is, of course, it's always possible to write down a thought experiment in formal symbolic form. However, before doing this, you need to see this visualization to get the idea. Right? Yes, it's possible. You can always formalize your intuitions. It is possible. But where are you getting them from? You are getting them from these thought experiments and visualizations, use of diagrams. And I think it's a very strong reply. I think this is how it happens in mathematics. And I will try to convince you in this claim as well. So, Lakatos and Brown as well, they have kind of broad view on what thought experiments are in science and in mathematics in particular. So their view is sort of a quasi-empirical character of mathematics. Mathematics is very similar to sciences, to natural sciences, and as in sciences we use experiments, as in mathematics we do experiments. So almost all mathematical thinking, because in mathematics we arrive to our conclusions solely by thinking, their view is that mathematics is all about thought experiments. So thought experiments are proofs and refutations of proofs. Remember, as in Lakatos' book, Proofs and Refutations, mathematics is a narrative which consists of proofs and refutations. Brown's view is very similar to Lakatos' view. And Norton thinks, as I said, that thought experiments and visualizations are simply illustrations of proofs, as in Landau's book on analysis. Remember, illustrations are just a lubricant for making it smooth and understandable for stupid students. So these are kind of two extreme points of view. That thought experiments are proofs, and another that thought experiments are simply illustrations. When you say they are illustrations, it means that the epistemic role of visualizations is very thin. Yeah, you only use them to illustrate something. Yeah, to make it brighter, looking better. Yeah, but when you say that they are proofs, as Brown and Lakatos do, this is a very strong claim on the opposite. Yeah. However, it's a strong claim, but the problem is it only focuses on proofs again. Yeah, as remember on the first lecture, I told you that there was this over-concentration on mathematics as viewing mathematics as a proof production enterprise and forgetting about other interesting things in doing mathematics. So I am trying to get back to this area which lacks attention of philosophers, and ask the question: how about other roles of thought experiments and visualizations? Could it be possible that they can play some role in discovery of new ideas, or developing new concepts, connecting domains? Could it be possible? So I will try to explore these three questions, three possibilities using the case study. And maybe you could suggest some more roles of thought experiments and visualizations in mathematics. Of course, it's a very interesting question, how a thought experiment could be possible in mathematics. Well, and what we shall count and what we shall not count as a mathematical thought experiment. If you take a point of view, a broad point of view as Brown or Lakatos, if you have an equation, for example, a linear equation, you can experiment with this equation and you can try different x's and different y's and see if they fit the equation. You can say, what if we take x equal 1 and y equal 2, what will happen? Would we count this as a thought experiment? Because in a sense you are experimenting with x and y, you have kind of question what will happen if, but would we count it as a thought experiment in mathematics? In this case, everything is a thought experiment in mathematics. Yeah. And it doesn't make the subject too very interesting. Yeah? No, it's not interesting enough for us. And by the way, what we are doing here is that we actually we are just following the algebraic rules of solving equation, a linear equation, right? It's just rule-governed manipulations. And I think for me this is a keyword, rule, governed manipulation. So I think that maybe an experiment is something when you really break the rules and you go beyond and you try something new and then you see what will happen. So I suggest the following assumption, what we can count for mathematical thought experiment. It's when experimental thinking is going beyond following the rules, and this is one point. And the second point, by using sensory imagination as a way of eliciting the benefits of past perceptual experience. What I want to say here is that let's count thought experiment, mathematical thought experiment, when we use some physical properties of this object. When we have a mathematical object, but we add some physical properties to it and do some physical manipulations with this object, and then we'll see what happens. So when we are doing this, we use our sensory experience, which we know already from reality, from our contact with reality. And somehow we use this knowledge to solve mathematical problems. So this is and this is where my heart is. So I'm trying to show you in a thought experiment how it happens. And the main philosophical claim about the role of thought experiments and in general cognitive representations in mathematics is mathematical representations play a significant epistemic role. Yeah. I mean, you can represent one mathematical object by another mathematical object. And of course, it's very useful. As I said before, you can have a geometric construction, but you can use Descartes' coordinate method, and you can code everything in numbers, in coordinates, and solve your algebraic equations. Therefore, you use mathematical representation, algebraic in this case, to solve geometrical problems. It's very useful. However, sometimes it is the cognitive representations which play a significant epistemic role. They may lead us to new resources. This is my proposal, and this is what I am trying to show you in the next few slides. So, here is an example of a mathematical thought experiment, MTE, I will call it further, a Cayley graph, a cycle graph, sorry, a cycle graph. If you can see, this is a cycle graph, so you probably saw it before. It consists of vertices and edges, and it shapes a cycle. What we need to learn, what we need to know, just a couple of notions. You may remember it from the previous lecture. The distance between two vertices u and v in a graph is the length of the shortest path between u and v. Yeah? You know that there could be different passes between two vertices. You can, for example, from this vertex you can go to this vertex by 1, 2, or you can go left around. Yeah, there are two passes in the graph, and the shortest one is this one, 1 and 2. The length is of the length 2. Then the diameter of a graph is the maximum distance between vertices in the graph. So you take all the vertices in the graph, you take all the shortest passes in the graph, and you take the maximum one. So it's kind of a size of a graph, in a sense that you can get the longest path, among the shortest. Yeah, is it? You will understand it better. So, given this graph, for example, you have a task to express the diameter of the graph in terms of the number of the vertices. So, let's say you have n vertices in this cyclic graph, and you want to say what is the diameter of the graph in terms of n. Is it clear? It's a simple task. I suggest a simple thought experiment. So imagine that the vertices of the graph are made of pearls. of equal size and weight, and adjacent pearls are connected by a fixed unit length of strong thread like a necklace. So I have a necklace, something like this. So you have the vertices of a graph would be pearls, and they are connected and they cannot slide, they cannot move along the thread. They are fixed, but they have weight. Yeah, they are heavy. And then imagine holding the necklace by one pearl, letting the rest of it go. What will happen? Yeah, I have pictures. What I mean, imagine that this kind of picture. You have a necklace and you just dangle it like this. So, what will happen? Well, I assume the diameter will be this. Yeah. It's straight away you can see what it is. So, yeah, something like this kind of necklace. Sometimes you have pearls, and in between you have this unit distance between them, and they don't move, and they're all the same. And this is the picture you draw. Well, then, if you look closer, what's happening? If you look at the end, what happened here on the bottom when you dangle it? Of course, in your imagination, yeah, not in reality. You imagine that it depends on how many vertices you have. Yeah, is it an even number or is it an odd number? If it's an odd number, you will have on the bottom you have this kind of picture. Yeah. If it's an even number, there will be one pearl dangling down. Yes? Usually this is called an antipode, something opposite, antipode of the given vertex. So this vertex on the bottom is an antipode of the vertex on the top. In this case, when we have an odd number of vertices, we have two antipodes. And in some more complicated graphs, we can have three, for example. So, how can we use this thought experiment? Well, we can calculate that the diameter for odd number is n minus 1. Yeah, we just remove this vertex divided by 2. Yeah, because when we dangle it, we try to put these pearls in front of each other, kind of shape them as pairs. Yeah, so we pair each pearl below the pearl which we hold in it. Yeah? So therefore we have pairs, and we already understand the situation on the bottom. That's why n minus 1 divided by 2, and in this case n divided by 2. Okay. So, there are 3 questions about this thought experiment. Is it an experiment or is it an argument? Reminding the Norton's objection. Is it reliable? Because Norton also say that they are misleading, these thought experiments. They are unreliable. And is it a mathematical thought experiment? Because somebody will say, oh look, you can run it in reality. Yeah. So the first question, the answer is yes. This is an experiment. Why? Because what we are doing, first of all, we are visualizing the graph. We are drawing the graph, and then we are visualizing it as as if it has weight, it has some physical properties. We are visualizing it as a physical object. And then we look closer what happens to the bottom of the necklace. I assume the first two steps are not so revealing. We are not learning anything new from the first two steps, but from the last one, I think we do learn something new. What we were given in the beginning, just a graph, we didn't know this information. But then we understand that there could be two situations, and they're different from each other, depending on the odd and even number of vertices. So we are learning something new from this experiment. One can say, is it reliable? Well, I think here and in most of thought experiments in mathematics, we usually use very basic physical experience. And it's so simple and clear that it's very difficult to make mistakes. It's so obvious. So I think we are able to produce reliable judgment in our imagination, as it goes in this case. And then one can say, is it a mathematical thought experiment? Because you are kind of, in your imagination, you are manipulating with a physical object. But I don't think it's a strong objection, because first of all, it's about mathematical objects, right? It's about a graph, or even group. Yeah? It is idealized because we choose not any kind of necklace, we choose particular properties. I mean, in reality, if you take any, it wouldn't fit the requirements of our task. We have to choose particular properties of this physical object. So it's really idealized, and the conditions are corresponding to our mathematical context and mathematical task. Maybe you have more suggestions on this question. It would be interesting to hear what you think about it. So this was a simple thought experiment, very simple thought experiment, which helps us to solve a simple mathematical problem. But in the next lecture, I'm going to give you a serious, very serious thought experiments from using graphs as well, but not from graph theory, but from geometric group theory. And it's a bit complicated, and it would be useful to learn one new concept, namely a Cayley graph. The graph you saw in the previous example is actually a Cayley graph. A Cayley graph is a graph of a group. Let me give you a little bit of historical introduction about Cayley graphs. It's called after Arthur Cayley, an English mathematician from Cambridge. Quite a remarkable personality. He was born in England, but his father was a merchant in St. Petersburg, in Russia. So Arthur Cayley spent his childhood, his early years in Russia. He married a Russian woman, and then he became a lawyer because his father wanted him. However, he was so passionate about mathematics, and he became a mathematician in Cambridge, and he has a very extensive number of writings, huge library. And he was working on application and connections between chemistry and algebra. And he noticed that there is a similarity between algebraic groups and chemical graphs. So his idea was that maybe we can study chemical elements by using algebra, and maybe we can find some connections. In particular, by enumerating chemical isomers, he suggested that we can draw graphs of groups and see how we can apply them. His friend Sylvester was the first mathematician who used the word graph in his publication in Nature in 1878. Chemistry and Algebra was the title of the paper. So, as I said, a Cayley graph is a graph of a group. What is a group? Maybe some of you know what it is. Let me just remind you that a group G is a set of elements with a binary operation. Binary means you always have two elements and an operation between them. Yeah? And this operation satisfies four group axioms. The first one is closure, so whenever you have two elements A and B from group, if you use this operation, I use this sign. What is it in Portuguese? This sign? Arroba? Arroba. Yeah, it could be a plus. Arroba. It could be plus, it could be a star, or a dot, usually a star or a dot you can find in algebraic literature. I use this one. So whenever you take two elements in a group and you apply this operation, you will create another element of the group. You are not going out of the group set. So that's why it's called closure. Whenever you apply the operation to the group elements, you are stay closed inside the group. Right? Then associativity, it's very similar to the algebraic arithmetical operation. So it doesn't matter if you first apply A to B and then C, or first B to C and then A. It doesn't change the result. And then, very important, there is an identity element in this group, such that if you take any x, any element of the group, and apply the group operation to this element and identity, you will have the same element. So this identity element doesn't change anything. Okay? And there is always an inverse element to any element of the group. So if you take, you have identity, because you have identity and all x in G, there is y in G, which is usually denoted like this, the inverse, such that if you apply the group operation, you get identity. Okay, the simple example of a group is the group of integers under addition. Group of integers under addition, usually denoted as Z plus. And the set of elements are all the integers, all the negative, positive integers, and 0. Why is it a group? Well, whenever you take any two elements and you sum them, add one to another, you'll stay inside the group. we have identity, which is what? 0, and we always have an inverse for minuses are pluses, for pluses are minuses. Okay. So this is a simple group. And cubic Rubik's cube is also an example of a group. Let's say it's a model of a group because each step, each move in the cube is actually a member of a group. Why? Because whenever you make a move, you can come back, so there is an inverse, and there is some initial element situation in the puzzle with which you start, yeah. And whenever you make moves, they are all inside. You can't. You stay inside. All the moves are kind of either inverses to each other, or identity, or a sequence of the same steps. What could be a non-example of a group?
It's hard to see how associativity.
Associativity.
Yeah.
In the cube.
Yeah.
Right, left, down, left, and first, and if you do left, and right, you have the same. Another example.
There's plenty.
Yeah, plenty. Well, for example, if you take only positive integers, it wouldn't be a group, right? Because you wouldn't have inverses. Very simple. Alright. As I mentioned before, there are mathematical representations. So we can represent a group by a generated group. By adding just a little bit of more structure to a group. What we need to know is a generating set of a group, which is a subset of the group, such that every element of the group can be expressed as a combination, of course under the group operation, of finitely many elements of the subset and inverses. So, generated group is just some elements of our group which can produce all the rest of the group. In our first simple example, if you take integers on the addition group, and for example, take a subset which contains only one element of the group, 1, we can produce all the rest of the integers just by applying group operation again and again. Right? For example, we can get 4 by plussing 1, 1, 1, 1. Right? And we can use the inverses to produce the negative numbers and 0. Yeah, is it simple? So now we can draw a Cayley graph of a generated group. How we do that? A Cayley graph of the group, usually it's denoted as K. So group Z, yeah, in respect to the generating set which contains only one element, yeah, and plus is denoted as K Z1 plus, has the following visualization. So the vertices of the Kelly graph are the elements of the group. Of course, it's infinite. It's infinite. I started with -2, -1, 0, 1, and so on. Yeah? And the edges are just application of the group operation and the generator. Yeah? So what we are doing, -2 plus 1, so and there is the edge is directed. It is directed because it shows that we are applying the right multiplication, right operation of the group, and it brings us to -1. Yeah? -2 plus 1 gives us -1. -1 plus 2 gives us 0. 0 plus 1 gives us 1. That's how we draw the Kelly graph. So all the vertices are the members of the set of the group, and application of a generator gives us an edge. The direction may be important because it shows how whether we are applying an element or whether we are applying an inverse of the element. For example, if we are in 0, how can we come to -1? Plus -1. -1 is an inverse of 1. So that's why we go against the direction of the edge. Okay. So now we know how to draw a Kelly graph of Z in respect to 1 is a set, a generating set. But you can notice that you actually can generate integers not only by 1 itself, yeah, but also by 1 and 2 and their inverses, and 2 and 3 and inverses. And the Kelly graphs will be slightly different, as you can see on the second and the third drawing. So here you have two generators, 1 and 2, yes, because when you have -1 plus 2 gives you 1. Is it correct? Yes. Or you can go to 0 by plussing 1 to -1. Yeah. So 2 generators, 2 different colors. Here I have black and gray. Black stays for +1 and gray stays for +2. Yeah, clear? Now here we have again 2 generators which are 2 and 3. Again 2 different colors. What they are, from 0 to 2, I assume it's +2, yeah? And the black one from 0 to 3 is +3. And of course inverses, because from 3 we can go back to 0 by subtracting, by plussing -3. So they are 2 different graphs of group Z in respect to different sets of generators. Okay. Mathematicians often say that visualizing groups by Kelly graphs could be very useful. You can read lots of information from Kelly graphs. Of course, here they should be small Kelly graphs. Yeah? Otherwise, when they're too big and they have many vertices, it's not extremely helpful. But when you have a small group, you can read some interesting information from graphs. Here is the cyclic graph you saw before. In fact, it is the Cayley graph of a cyclic group CN. And there are the others. So, observing these Cayley graphs, we can notice some interesting properties of them. For example, you can see that they are all connected, right? All the vertices in all Cayley graphs are connected. Another thing, you can notice that they are regular. You can see that each vertex has the same number of edges and the same number of colors and the same number of edges with a particular direction. Right? For example, this Cayley graph. We have one blue vertex going out, one getting in, and this is true for all the vertices, this and this and this and this. Yeah? Of course, you remember that you always can change the drawing. You can stretch it, you can kind of move the triangles around. Of course, quite often we prefer them symmetrical. You can make the edges round, not straight. You can drag the inner triangle out of the triangle. Yeah. What does it mean that you have double direction? It just means that you can go back and forth by the same generator. So it's a regular graph. You have the same number of vertices and edges. But even more to that, if you look at them, all the vertices are kind of the same in a Cayley graph. Yeah. And this is what is in a formal way is called the vertex transitive. It means that actually it doesn't matter how you label your graph. I did label the previous graphs, Cayley graphs, for Z. I put integers 1, 2, 3, 0, minus. Yeah? But in fact, you don't even need to do that. You only can draw a line, put the points on the line, and you can always recover the integers on the line, right? Because we can take, here is a label graph, 1, 2, 3, yeah? But it's, we can change this labeling. You can see it from the, just by observing visualizations, that it doesn't matter how you label your graph, right? Where you put the identity in which vertex. If you have an unlabeled Cayley graph, you can always recover all the elements of the group. For example, you can take as an identity the first one, yeah, and then you can see what you do. You can let me maybe come back to this. Imagine that we have no labels. Yeah, we only have dots. We can take any of them 0, and we can always put in 0 here. We can always understand that this would be 1, minus 1, yes? Because we have to go against the direction, which means we apply the inverse, and the generator is 1, only one generator, so it's 1. That's how we can recover all the elements of the group from the graph, even if it's not labeled. And it's unimportant for us how we labeled Cayley graph. This is a very interesting property. By the way, talking about pearls, you didn't stop me. You didn't say, you have this formula and divided by 2 for diameter. But would it be, how about generality of this formula? Would it be true for any n? Yeah? Yes, actually, it would be true for any n, because you can take, doesn't matter which pearl you take, to you can take any of them and you will have the same situation. Yeah. And the same for Kerry graph. That's how we can say, if independently which vertex you take, you will have the same diameter. This is the same length, and this is as this, right? And as this. So, which means that diameter is invariant in respect to labeling of the graph, and the antipode too is invariant. Yeah? I mean, the antipode for a particular vertex. Yeah. So this is what we can observe from drawings of Kerry graphs, some new information, and let me talk a little about a little bit more complicated graph. As I said, Rubik's cube moves shape a group. So the elements of the group are moves of the cubic Rubik cube. So, and then we can draw a graph. We can draw a Kerry graph of the puzzle. Here, each vertex of the graph is the situation of the puzzle. Yeah, and when we make a move in the puzzle, we draw an edge in the graph, and we are getting to a new move, which is another element of the group. Right? And therefore, all the moves all the situations in the puzzle are connected by the moves of the cube, right? So, therefore, we can draw a graph of a puzzle, and we can study a puzzle by using a graph.
But you mentioned that when they are too big, sometimes the graph is not that helpful.
Absolutely, you are absolutely right. Yeah, it makes sense.
We are in the
absolutely. You're right. Yes, yeah. But you know why I use this simple example with the pearls necklace with the cyclic graph, because it's a nice introduction to a more complex things, and it's always good to have a simple example first, and then you can better understand the complicated cases, yeah, by analogy, let's say. So you're right. Sometimes it even doesn't make sense to draw a graph. Sometimes it's impossible to store your graph in the computer memory. But in some cases it's good. And this is another puzzle, not a Rubik cube, it's something different. It also has each step is a permutation of 4 elements, you can see. 4 things. These are not 1, 2, 3, 4. These are not elements of the group. Be careful. Yeah, they are some elements of the puzzle. Yeah, like in a Rubik cube, we have edges of different colors, and we move edges. But the move is the element of the group. Here as well, the permutation is an element of the group. So we change 3 and 2 and 4, and here we change them again, but 1 stays the same. This is a permutation, and this is the move. We draw an edge in the graph. Well, it doesn't matter. So there is this nice Kerry graph of a puzzle. We can see that it's symmetrical. I'm sorry the edges are not so visible on this background, but you can see it. Here I redraw a graph in such a way that I don't preserve the permutations anymore, but I trace the levels of the graph. So this is the point, the pearl, which will be in the top. If I want to hang handle the graph. And this is the yellow is the next level, and the orange are the next. And then I can see that this red will be on the bottom, will be the antipode for my blue vertex. And that's how it will look. It's like a kind of a net of oranges, or a net of oranges or something. So this is a more complicated graph, but again we can depict it in this way that we kind of see the structure of our puzzle. Yeah? What does it mean to solve a puzzle? It means to find a path between some given position to an initial position, an identity, element two, when the puzzle is solved. And presumably we want to find the shortest path. Yes. So we want to find a diameter of the graph. And we can see that from these visualizations, first we have the growth of the steps. We have more steps, and then they collapse to one. Yeah. So we see the dynamics of the puzzle, and we see that there is only one antipode, and we know that the graph is vertex transitive. Doesn't matter which position we start. There is always the length of the diameter is the same. The diameter is invariant to labeling. So what we can learn from these thought experiments, there is a unique antipode in the graph. An antipode in a Cayley graph is invariant to labeling. This is actually just about finishing the lecture. What we have discussed today, we have discussed thought experiments. I gave a short introduction, what they are, what are the main properties of thought experiments in mathematics, and I was trying to show that they play important epistemic role. Well, in my case study, there is some epistemic role. Maybe it's not crucially important. We can get some new information about the structure of Cayley graphs, or a structure of a puzzle, therefore a structure of a group, an algebraic object. So in this case, we start with a very abstract algebra. At the end, we have an experiment with a physical object. We are getting some new knowledge. We are getting some ideas about the structure of Cayley graphs, that they are vertex transitive, and we can relabel them in any way. We can prove it in combinatorial way, but the idea can come from visualizations solely. And we learned what Cayley graphs are, so I think that's it for today. How about the questions? Any questions, please? Yes.
Might be not very silly, but all the generators you mentioned, they had a difference of one, and that's the case that every generator, they should have one. The difference between the elements of the generators are one.
No, I don't think so. No. I mean, in different groups, the generators could be, if you take let's say, you can think of Z, you can try different sets of generators. By the way, the group itself, the whole group, is also a generator, Group generates itself. If you take, let's say, a triangle with equal sides, you can transform it by reflection, flip, and by rotation. So this could be two generators, right? Because if you rotate a triangle, it stays the same. You don't change. Rotation on 3 p over 3 is one of the generators, and flip is another generator. By using these generators, you can produce all transformations of the triangle, which keep it symmetrical.
Perhaps I imagined that you were saying that for the integers, for instance, there are some subgroups that are not generators, right? For instance, if I take 2 and 4, it won't take the odd numbers, right? You won't with the inverse operation. Perhaps the difference should be odd, I don't know, but there are subgroups that are not generators, right?
Absolutely, yes.
The MGC has to be 1.
It should be 1, right?
Yeah, the difference should be 1 because you need to generate one somehow.
If you can generate 1, then you can generate that.
Yes.
Yes. That's it.
Like the difference between some of them.
At least one difference.
Yeah.
I would have a doubt about the example about taking a necklace, a pearl necklace for a cyclic graph. So should we imagine it necessarily as a physical object, or could be there something as a direct imagination of a graph? Like when I see the image of the pearl necklace, yes, I can imagine the antipode, but couldn't I imagine directly the graph? If I represent a graph, what is imagination about the graph finally? Because I was thinking it's a quasi-empirical approach to mathematics, but finally in this, aren't we giving up the a priori, a posteriori distinction? What characterizes specific mathematics there, and not a proto-physical investigation about the nature of necklaces or about the nature of a topological of nature itself, and not a pure topology or a pure study of graphs of mathematics? I was wondering about that. Is it necessary to think physically about this example, or couldn't I imagine directly about graphs? For thinking there is an antipode and I can have the diameter as half of the number.
Well, of course you could do it without a thought experiment. For example, you could count all the edges and then calculate it. Yes, in a kind of combinatorial way. But you could make a mistake. It could be an error-prone way, and it could be tedious as well. Whereas when you're, it could be not pearls. It could be something else. In fact, this thought experiment, the final one, it's not my invention. It's from a mathematical paper. So that's what mathematicians are doing in practice. I think what is important here is you are imagining that your graph has weight. So you're imagining this dangling down shape, and you see that there is an antipode dangling down. It always will happen. This physical sensory experience, just make it quick, and yes, it gives you the idea very quickly. What else? Yes, it gives you an image how the puzzle grows. For example, on the first level you have less, on the second level you have more and more steps, and then they collapse to one suddenly. So you have this scenario how your puzzle is going. You could do it combinatorially. You would need a computer, or you would need some tedious calculations. Here you have an image straight away. You know what to do.
And when you do mathematics as this, is the a priori, a posteriori distinction abandoned? Can I say that I'm doing mathematics with physical objects? Is it possible to say this?
is it dependent? Well, mathematicians of course don't think about this, but for philosophers, is it an a priori knowledge or is it an a posteriori knowledge? You do use your physical experience, but it's very limited in this case. It's very elementary, and in arithmetic, for example, in elementary arithmetic, I think we do use a posteriori knowledge, and some parts of mathematics could be not a priori, could be a posteriori, but here we don't rely so much on this physical experience. We are getting the idea, and yeah, it's very elementary, as I said. It's very clear. Clearly, we see that there is either one antipode at the end, or either two. Is it a posteriori? Yes, I think so. But you can also prove it a priori. Thank you for your question.
I think if I can say something else about it, the model of this necklace, which is physical and it's not a priori, but you take it as a model and you have some conscience, you know that you're not dealing with the physical thing, you're using that for dealing with abstract thing, and you know what you can abstract from the physical thing, and therefore you're not dealing with the object, you're just...
Okay, so in this view, finally, mathematics would be a priori, and the physical object is just an illustration, right?
Yeah,
that's why what I was... Because
like that,
it would be an argument for the objection, right? To say, I know this physical object is just an illustration, but you could handle it without it, finally, right?
And the point is to know that which properties of the object you can abstract.
Yes, yes.
You're not dealing with this.
Yes, I think the gravity property, as you said, is important because it's a physical property that perhaps helped me to think of the antipode in the other side.
Yes, first of all, you have a high control over your experiment, not like in reality. You choose you choose weight, you know what you're doing. Yeah, because in reality, if I use this, at this end, it's not very clear where is the antipode. Yeah, it's just I have to do something else. But in our model, everything is idealized. However, we use these particular physical properties, such as weight, to strengthen our mathematical thinking. Yes.
Yes. But even about the definition of thought experiment in mathematics, as you went through, there is in philosophy, in physical. In mathematics, I think it depends perhaps on the ontology that we pretend for mathematics.
Mm-hmm.
Because if I am a Platonist for mathematics, I could make a thought experiment about a mathematical object that in fact does not exist. But if I am more of a constructivist in mathematics, if I imagine an object, wouldn't it exist immediately? So every mathematical development would be already mathematics, even if a thought experiment would be already mathematics in fact. Wouldn't it be like to characterize a thought experiment in mathematics would be something dependent on the philosophy of the ontology of mathematical entities, I presume?
Yeah, it's a good question. For example, for a Platonist, I assume you can model anything in mathematics. And in this case, any modeling would count as a thought experiment, right? But if you are a constructivist, as you say, you only can you're only allowed to use things which you can construct, which exist. But you can construct them in imagination. And then if you can formalize your imagination, then you have a proof and an algorithm, then it's alright. Yeah. Yeah, I think so. Well, I think it's interesting that dealing with abstract objects, like algebraic objects, for example, nevertheless, we can apply our empirical experience and physical properties. These are, I think, are interesting cases in mathematical practice. How is it possible, dealing with absolutely abstract objects, somehow end up talking about oranges and get a solution from these thought experiments? This is very interesting. Thank you so much. See you next time.